All right, let us begin. Good afternoon, everybody. Well, two of you. All right, before we get started, in light of recent events, let me reassure you that I checked this morning, okay? 2 plus 2 is still equal to 4. Triangles still have 3 sides, right? Math still works. We can still work with it. We can still learn and go about our business no matter what the politics try to say about our lives, okay? And most importantly, God is still good. So let us use that as our driving force moving forward, okay? Now, that said, let us, as we've done this week, go back to yesterday's work and check our answers, see how we did. We were doing parallel lines, finding the angles inside those relationships, all good stuff. So here's the first set of answers. And let's see, somebody chimed in. Who just joined in? Got Angelina now and David, both cutting it under the wire. All right, but we got everybody. Good. All right, so 1, 2, and 3 had you finding the angles, knowing the lines were parallel. 4, 5, 6 gave you some angle measurements, and you had to decide if they should be parallel. 4, yes it was. 5, not so much. And 6, technically, just on what we know so far, you cannot be determined. But I'm making a note here to come back later, because I suspect we might be able to determine for sure if these are parallel or not, if we only had a few other pieces of information, some other conjectures and geometry relationships that we could use to apply in this case. I think we can do it. So I want to come back to that. Anyways, moving along this page, here's number 7. I tried to put all the measures as close to their appropriate letter as possible, so the 58 is for F and the 26 for E. I believe you can read the rest of those. And then finally, number 8, X is equal to 80 degrees. And on 9, X is equal to 20 and Y equal to 25 degrees. Any questions from those exercises? No? All right. Then let's trek on. Next step on our geometric journey is to combine these angles and lines to form some actual shapes. Let's talk about the angles inside of polygons here. Right? We got to try to figure out something like these guys. Right? So to do that, what do we know that could apply to the angles of polygons? Well, there's a couple relationships we can figure out. We can determine something about the interior angles and something about the exterior angles. And in both cases, we're going to start with a couple simple things that we know, and I want to build up from that to kind of deduce something about the interior and the exterior angles of polygons. I'm not quite writing a full-on proof, but you could think of it that way. I'm creating a justification for these new facts about angles and polygons. Okay? So what do we know already? Well, we know that a straight line, all lines are straight, any line could be thought of as a straight angle, a 180-degree turn. From going in this direction, spin right around, face the other way, that's 180 degrees. And so likewise, two angles inside a set of parallel lines we established generally any acute and any obtuse could combine to make 180 degrees. They would be supplementary. And so specifically, we can take the two next to each other on the inside, the consecutive interior angles, okay, or CIA for short, because they are on the same side, and they're both in between the parallels there. These two will be supplementary. And so think of this as if you face that way, you walk down, turn the block, and then go back the way you came, you've made a 180-degree turn, right? Two lefts make a U-turn kind of thing. Now what if we extrapolated from there? Make an even bigger shape. Put two pairs of parallel lines together. Now we've got a parallelogram. Right? These two lines are parallel. These two lines are parallel. So any pair of lines in here, you could say, hey, those are CIA lines, or CIA angles. So these two angles make 180 degrees, right? And on this side, we've got two angles between parallel lines, one acute, one obtuse. These are two CIA angles. They add to 180 degrees. So what is the total of this angle plus this angle plus this angle plus that angle? All four of them together are going to add to what?
$360.
360, thank you. Eileen, yes? Very good. 360 degrees total. 180 plus 180 equals 360. Okay? You're going to hear those numbers a lot. We're going to be adding 180, 360, doubling, halving. Okay? Get used to the number. It's going to be your new favorite number when we're done with geometry. All right, so all four angles in a parallelogram will necessarily have to be add together to 360 degrees by the properties from those parallel lines, right? From knowing this about CIA angles and parallel lines, we get 360 for a parallelogram. That's pretty nice, and we could write that up as a formal proof, and we could make a full-on justified argument why it has to be right. And so now I'm going to extend out a little bit more. This one is not completely justified, but I think you'll see the idea here. Because a parallelogram is not as universally useful. Instead, I would like to cut that parallelogram in half. And we do so very specifically. I'm going to cut it from one corner to another into two triangles. Okay? And you can see you can do this to any parallelogram. Just connect the opposite corners. You will always get two triangles. And in fact, you will get two matching triangles. Very cool. I'm not going to prove that one here, so this is why I don't have the full proof argument here. You're going to have to go with me a few steps. But I think you can at least see with the angles. That's all we care about right now. The angles will be the same. Right? I've taken all four angles. They're still there. I've not added any new angles. I've not taken any away. So we haven't lost or gained any more degrees. It's still a full 360, except half of them are over here and half of them are over here. Right? I've just taken this angle, divided it into two pieces. This one got divided into two pieces. But if you say, hey, wait, this piece is bigger than that piece, that's okay, because symmetrically over here, I have the same angle, and now the big piece is on the other side. All right? So we know these ones were congruent to begin with. So I think it's pretty safe to assume that this should be an exact half, 180 degrees, at this point. Yes? Does anybody completely not believe me at this point? Again, this is not a full formal proof. We would need some more stuff here. And in fact, I'm going to generalize even further. As long as you're letting me, let's say we'll call this the triangle sum conjecture. The sum of the interior angles of any triangle is 180 degrees. Any triangle? Really? That sounds a little suspicious, Mr. Apple. I mean, I get that, okay, you divided the parallelogram in half, but any triangle? What if you didn't start with a perfect parallelogram? That sounds suspicious. Like, there's no way it can just always be the case. What about this one? What about that one? Okay? We'll explore that more on Friday. If you're not 100% settled with it, we will make an extra effort on Friday to prove that triangle sum conjecture should absolutely be accepted for any triangle. Okay? We haven't proven it yet, but we will on Friday. But this is a really big deal, because if we can get with absolute certainty the sum for a triangle, as you saw the parallelogram, well, that's just two triangles put together. And in fact, any shape is multiple triangles all put together. Everything can be composed out of triangles. If you don't believe me, look at the nearest video game with 3D graphics. Everything in there is composed of triangles. That's actually how the computer thinks of it. It's all triangles. Yes, even Minecraft. I'm aware it looks all like squares, but in fact, every square in Minecraft is two triangles. Okay? So with that in mind, can we find the interior angle sums of other polygons? Absolutely. Right? We're just going to work backwards like we did. We're going to take, say, a rectangle, and we'll cut it into now the two triangles. So this rectangle had 180, this triangle is 180 degrees, this triangle is 180. So altogether, from that now we build back up to 360 degrees. So we're going to create a little table here. For a four-sided figure, we can cut it into two triangles. And then the sum is 2 times 180, or 360 degrees. And if it's a regular shape, that is to say, all of the angle measures are congruent, you would take that total of all the angles and divide by each one. 360 divided by 4 angles inside would be 90 degrees apiece, right? And we kind of already know that about, hey, yeah, that would be a square, right? They're all 90-degree corners. It works out. So let's do this for a few more, and let's see if we can find the general pattern for any n-sided figure. How about a pentagon? How many triangles can we draw? If we were here in person, I would have you guys get out paper and you would draw this and measure it, and we would test it ourselves. We don't have enough time. Here we go. I've got a pentagon up there. It doesn't have to be regular, but we could connect 2 points here. We could draw a triangle there. And well, I could connect these 2 points here and make another triangle. Now I got 1, 2, 3 triangles, and then this four-sided shape. Oh, wait. I'm not allowed to do that, because now I've created another set of angles in here, right? We can't create any additional angles. We only want to count what's already there. So do not intersect any of your lines, okay? Do not create more shapes. You can only cut up the existing angles. If you cross through and make angles anywhere else, that's not valid. So we could divide the pentagon that way, or if you wanted this one, you could go that way and that way, or maybe this side, right? Not a lot of possibilities, especially if you rotate it around, it'll always look the same some way or another. But the minimum number of triangles you will create will always be 3, right? If we only cut up the existing angles, we can create 3 triangles out of a pentagon. Each triangle is 180 degrees, so 3 times 180 degrees gives us a total of how many degrees in the pentagon?
360.
No, that was for 4 sides. We're on the pentagon now. 3 times 180.
540.
540, thank you, David. 540 degrees now. Just look at them, compare them, right? These all look bigger than that one, don't they? So if you add them all up, shouldn't they all be bigger? And shouldn't each one be bigger? If we take 540, and divide it by 5. What do we get? Let's hope that's a little more than 90. It looks like it should be more than 90. Is our intuition correct? Somebody run the numbers.
108.
108, thank you, Carla. 108 degrees in a regular pentagon. So if you make all the sides and angles the same, each one inside will be 108. That's pretty good to know. I bet you some architect had to calculate that when they built the really big one in Washington, D.C., right? The Pentagon, you know? You could measure, you could check. All right, how about 6? What about a hexagon? How many triangles can I cut this into? This is definitely not a regular hexagon. In fact, it's not even a convex hexagon. I made a dent in the side here, but it still holds up. Check this out. Pick a point. We can draw from there. Can we draw from each? That's a little bit of a bendy line. Yep, we can just reach it. And there. Are those all triangles? Yep. 1, 2, 3, 4, that works. Let's try another way. What if we went straight across first? Ooh, then I could divide them up like this. We can divide it up like that. They don't all have to come from the same vertex. 1 triangle, 2 triangles, 3 triangles, 4 triangles. So I'm still getting 4 triangles out of it. All right, 6 sides, I can make 4 triangles. 4 times 180 is?
720.
720, thank you. Right, 2 circles all the way around. And then 720, you know what's coming, divided by 6 equals?
120.
120. Very good. What's the pattern so far? Can we skip to 8? What do you notice? From 4 to 2, 5 to 3, 6 to 4. How many should there be for 8 sides?
Adding 2. So
Adding
10
2?
triangles. I mean subtracting 2.
Subtracting 2, there you go. So it should be how many?
6 triangles.
6 triangles. Good. Well, however many sides you have, subtract 2. So for the 8, it would be 6 sides. And then we take that number at n minus 2, and we're always multiplying by what? 180, right? So what is 6 times 180? It's a lot. What was that? 1,000 something?
1,080.
1,080? Doesn't seem right. I thought it was 2,000 some. Someone double check for me.
I got 180, 1,082.
You also got 1,080. Really? Six times 1, 1,080. We got 2,000 some in the other classes. What did we do wrong there? I don't know. I'll have to look into that. Anyways, I'll believe you. So, that's the sum. That's all of the angles put together, regular or irregular. And if it is regular, and we can evenly divide it into all 8 of them, what do we get per corner?
135.
135. Good. And so in general, you would take that 180 times n minus 2 and then divide by n again. Let's put a box around those final formulas there. Those would be good to know. You don't have to memorize them. I will not be asking you on a test explicitly what is the formula, but if you know the formula or have it in easy access in your notes, you can look it up. It can save you a lot of time, right? On these exercises in particular, like, oh, that's a 1, 2, 3, that's 5 sides in there. Okay, 5 minus 2 times the 180. And if you don't remember the formula, at least remember how we came to it. 2 facts. That's all you need. First, the sum of the interior angles of a triangle is always 180. Every triangle is 180. And second, every shape can be divided up into triangles. If you know those 2 things, you can do anything. All right, any questions there on interior angles? No? All right, then let's talk about exterior angles. There's a lot of possibilities for exterior angles. We could have talked about this angle out here, right? The exact opposite of the interior angle there. That would be pretty straightforward. You would take 360 minus the interior angle, right? Just reverse it. But we're not looking for that. That's the reflex angle. That's not what we're talking about. What we're talking about here is like this diagram where I've extended the sides. Instead of just the little segment I need to make the shape, I've extended it beyond. Except I don't even want to do that much for all of them. Because notice if I extend both directions past a vertex, and I have a full intersection of lines, and I get 4 angles, one of which is inside. The red angles are all inside my pentagon. And I get 3 angles outside my pentagon. That's too many. We don't want all of that. We want to count only the clockwise angles or all the counterclockwise angles. You could go the reverse direction. What do I mean by clockwise? Well, picture this. This is your block that you live on in your neighborhood. The lines are streets, and you're going to go for a walk. You go head out your house, and you walk down to the first corner. The street goes on. Another street comes by at the intersection. So I'm going to turn this way, right? And you're turning. You're facing that direction, and then you turn to face this direction. So the angle represents an amount of turn. That's effectively what every angle is, really. It's a measurement of turn. Okay? And so you turn, in this case, in the clockwise, you're turning this way around a clockwise circle. And then you walk to the next intersection. And you turn from this way, turn to face that way, you turn this much. Then you walk again, and you turn again. And you walk, and you turn, and you walk, and you turn. And then you get back to where you started. So, adding all of those turns up, I have a pentagon, I have 5 exterior clockwise angles, the sum of which will always be how much? Carla says 360. Does anyone agree or disagree? Think about this. I'm going to take a walk on my teeny tiny block around the chair here. I'm going to start this way. I'm going to head out. I'm going to stop, and then I turn. And then I walk this way. And then I reach the next intersection, and I turn. And I walk this way. Next intersection, I turn. Oh, hey, I'm back to where I started. Because I went all the way around my block. If you turn, no matter how many turns it takes you, if it's a triangle, it's only 3 turns. If it's a hexagon, it's 6 turns, whatever. you still turned all the way around, didn't you? Didn't you make a full circle? You turned around until you were facing the same you started. That's 360 degrees. She's absolutely right. The sum of the exterior angles of any polygon is always 360 degrees. That's kind of cool. The interior ones, they all change. They grew with the number of sides, but the exterior always stays the same no matter how many sides. Here's another way to look at it. Here I have that pentagon with the extended sides, and I'm shrinking it down, making the pentagon smaller and smaller and smaller until it's just a teeny tiny point. Shrink it down to a single point, and those exterior sides, those exterior angles now all merge together into being adjacent angles to themselves, and I can add them up directly, and you can see that they all combine to form all the angles about a single point is a full circle 360 degrees. Put that on your Cheerios. Any questions there? No? Okay. Then, armed with nothing but those two facts, and the ones prior, of course, you can't forget the old stuff, you are now fully equipped to work through these practice exercises for today, finding all the angle measures inside such strange objects like this funny-looking pentagon here. And, well, we know what all of them should add up to be. So if you can find 4, you could subtract those off and find the 5th one, right? You can see, hey, D and 97, that's a linear pair. You can find that. Hey, this is a triangle. I know what the triangles has to be. It's isosceles. So, in fact, I know these two have to be the same, right? You got that symmetry going on. That should help you out a lot. So work your way through this. Ooh, when you get to 6, look at 6. This is a good one. All right, we got all 3 regular shapes here, triangle, square, regular pentagon. All those extra markings, looks like a porcupine of a shape now. But you can calculate what this angle needs to be, what this angle needs to be, what this angle needs to be for each of those shapes, because they're all regular, right? And then notice this angle plus this angle plus this angle all makes a full circle, 360 degrees again. So subtract those 3 off, and you'll be left with A. A lot of people forget about that. So I wanted to draw your attention to it. Okay, all angles around a single point are 360. But with that, then, I will leave the rest up to you. And you have about 17 more minutes to work. Go for it.